everyone, and welcome to this module on Introduction to Continuum Mechanics. So basically, from now on, we will record each principle, each field equation in a separate video, and we also devote a number to a number of module for that principle equation. So we basically, as I told you in the previous module, we used the Reynolds transport theorem to derive and to develop these field equations or principal equations. And we first start with the principle of conservation of mass. So basically, based on this principle, we may say that uh, if we select a fixed part of a material, so this part of the material should be constant at all time. So its mass does not increase or decrease. The rate at which the mass is increasing is always zero. So basically we have the material derivative of rho x t dv over material volume is always zero. So if I write also the Reynolds transport theorem, so we know that if we have, so let me just write in here just as a reminder, Reynolds transport theorem. We basically had the material derivative of a tensor field. Here we have rho, for example, it's a scalar field, so it's a zero order tensor. So the integral, the material derivative of the integral t x t dv over material volume is equal to the integral of the partial derivative of x and t with respect to time dv over the control volume, and this is plus the integral of t v dot and ds over the surface control. So this is the normal to the surface and this is velocity, which can also be written in the form as the material derivative. If we change this partial derivative to the material derivative, dt x and t, the material derivative of t, plus t divergence of v whole dv over the control volume. So basically, now we're going to write this equation using these expressions here, using the Reynolds transport theorem. So we have this in here. So this is equal to, so I'm gonna maybe write this 0 in here. So 0 is equal to, so we have the partial derivative of rho x and t with respect to t dv over vc plus the integral of rho v dot n ds over sc. So then we can take this to the left hand side of the equation, or we can write it as the integral of the partial derivative of rho x and t with respect to t over vc dv equal to minus integral of rho v dot n ds over sc. So what does this mean? So basically it says that the rate of the change of the mass, because this is the mass, so rho dv is mass, so the rate of the change of mass inside your control volume is equal to, and look at this minus sign, to the mass influx, or the mass that enters from the boundary. So we can write this as the rate of increase in mass inside the control volume is basically equal to mass influx, because we said that the book actually used the minus sign to say that something that hit, or for example, if hit enters the boundary, or for example, work is done. So we have minus, is equal to the mass influx, or the mass that enters through the boundaries. So if I use the divergence theorem to basically change this ds to dv, so we use the divergence theorem. So we will have this integral of rho v n ds over sc, to write it as, so this becomes the divergence of rho v dv over vc. So we can rewrite equation 1 as the partial derivative of rho x and t respect to t dv and plus, so we have the divergence of rho v whole dv over vc is equal to 0. So, and based on the principal lemma of calculus, if this is going to be true for every vc that we write in here, so this is going to be equal to 0. So then we have partial derivative of rho with respect to t. I'm not going to write x and t again, like I forgot to write it down here also. So let me just write it this like this. So then we have this plus the divergence of rho v equal to 0. And this is basically, this is the partial derivative form of the conservation of mass. So we call this the partial derivative of the conservation of mass. And of course, it is in deform configuration. So we can also use d of what we have, dt, the material derivative, is equal to the partial derivative of that that quantity plus its gradient v. So using this, we can write the above equation as, so basically if I open this, open up, so we have the rho, partial derivative of rho with respect to t, plus partial derivative of rho with respect to xi, or divergence I, v, plus this is going to be I, plus rho, partial derivative of vi with respect to x I is equal to 0. So this is going to be d rho dt, the material derivative of rho, d rho dt. Therefore, we have the material derivative of rho plus rho, and this is the divergence of v. is equal to 0. And this is basically the material derivative of the conservation of mass in the form configuration. So, and you should also remember that this basically in here is the integral form of the conservation of mass. In the form configuration. All right, so now we're going to solve example 7.5.1. So in this example, we have we have 6 parts, sorry. So we have a motion like x1, it's one-dimensional, 1 t, capital X1, x2 is equal to x2, and x3 is equal to x3, where rho is equal to rho 0 divided by 1 plus alpha t, and rho 0 is basically constant. So part A actually wants us the velocity field. So for the velocity field, we know that vi is the material derivative of xi with respect to t. Therefore, we will have dx1 with respect to t, the material derivative dx1 dt. So this is going to be alpha x1. So next we have dx2 with respect to dt, which is 0, and then we have the material derivative of x3 with respect to t, which is also 0. So the next part actually wants us to check the continuity so for the continuity we have to check this equation here. So we have either this equation or this equation because they are in the differential form. So if this one is correct, so we can say that we actually fulfilled or satisfied the continuity equation here. So we have the conservation of mass in material form. So the material derivative plus rho, I'm mistaken, rho divergence of v is equal to 0. And we also have the partial derivative of rho with respect to t plus divergence of rho v. So here we're going to use the partial derivative. It's much easier. So we have the partial derivative of, so we can use either of these. So it is rho. Rho is rho 0 divided by 1 plus alpha t. Then we have the divergence of this. So it is, if we open up, so we have partial derivative of rho, which is, sorry, this is xi, and this is rho 0, 1 plus alpha t. Then we have v plus, then we have rho, and it's the partial derivative of vi with respect to xi, which is equal to. So if I take this, take the first partial derivative, so we'll have minus rho 0 alpha divided by 1 plus alpha t squared. Then if we have x1, so we have nothing in here, so it becomes 0. Then this is going to be 0 because we have no expression here for rho that can be differentiated with x1, x2, or x3. Then plus, then we have this expression here, so it's rho times, so it's rho, which is essentially, let me write it down, like rho 0, 1 divided plus alpha t times partial derivative of vi with respect to xi. So we have rho 0 divided by 1 plus alpha t. So partial derivative of 1 with respect to x1. So if I write this, if I replace x1 from here, so I'm going to have alpha x1 divided by 1 plus alpha t. And this is going to be alpha. So if I take the derivative of this with respect to x1, alpha divided by 1 plus alpha t. And then I have partial derivative of v2, which is 0, with respect to x2 is 0, and v3, its partial derivative with respect to x3 is 0 also. So this is going to be 0 because this also is rho 0 alpha divided by 1 plus alpha t squared. So this is satisfied. So part C says that you have to compute the total mass. So then we have the total mass. And also the rate of increase of mass. So basically for this, we select a kind of control volume because we have a one-dimensional problem. And it changes from x1 equal to x1 equal to 1 to x2 equal to 3, as the book also said. And here we have a constant cross-section A. So the total mass, like the control volume, we already said that m is a function of x1 and x2, small both, and t is the integral of rho x t dv from x1 to x2. So we have this x1 and x2 from 1 to 3, from 1 to 3. Then we have rho 0 divided by 1 plus alpha t, which is necessarily our rho. Instead of v, we know that this is also dx. So we have a dx1 because we know that we are only using this in one dimension, so it is just x1. So then we have rho 0 a divided by 1 plus alpha t, x from 1 to 3, which is equal to, so 2 rho 0 a divided by 1 plus alpha t. So next we have the rate of increase of mass. So the rate of increase of mass is rho m with respect to t, which is equal to, so it's basically the partial derivative of this. So 2 rho 0 a 1 plus alpha t. So this is equal to the minus 2 alpha rho 0 a divided by 1 plus alpha t squared. And this here shows an increase in mass because we have mass inflow or mass influx, or the mass enters. So we have this as the mass influx, or mass is increasing. Next, we have part D, which says that we want to know the rate of mass inflow. So in order to know the mass inflow, we need to take the derivative with respect to we want to know how fast mass is inflowing and outflowing. Therefore, we will have basically v1, v2, and v3, the velocity. So if I draw again my control volume, we know that we have this is x1, this is x2, and this is x3. So we know that v1 is alpha, capital X1, v2 is 0, and v3 is 0. So this shows we have no contribution from the laterals like x2 and x3. So we only have contribution from x in x1 direction. So if this is A, we have here x1, and there we have x2, and this is x1, 1, and x1, 2 in here. And these contributions actually comes from these sides. So basically the mass inflow from x1, 1. So it's the surface. So we have rho A. That's why we use rho A, because the mass enters from this. So then we have also, since this is the rate, so we have also the velocity in here of x1, 1. This is equal to, so we have rho 0 divided by 1 plus alpha t. Then we have A, and we have alpha x1, which is equal to rho 0 divided by 1 plus alpha t A. And alpha and x1 is let me see, is this one, x1 divided by 1 plus alpha t. x1 divided by 1 plus alpha t, which is rho 0 A alpha divided by 1 plus alpha tx t squared x1. And since x1 is x1, 1, and since x1, 1 is 0, oh, sorry, it is 1, this is 3. So this is going to be rho 0 A alpha divided by 1 plus alpha t squared. So next we have the mass inflow, which is basically mass outflow, but let's write it this way. So we have x1, so maybe it's better to write outflow here. So this is going to be rho AV x1, 2. This is equal to, and since this is inflow, so this is going to have a minus sign, but we will put it later. So, or maybe I can just put it right now. So minus, 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 and you have to be careful about this since this is inflow. So this is x1, 2. So we have rho 0, 1 plus alpha t A alpha x1, and it is basically the same. So but instead of x1 in here, we will x1, 1, we'll have x1, 2, which is 3. So we will have 3 rho 0 A alpha divided by 1 plus alpha t in here squared. So then the net rate of mass inflow or outflow, outflow is this one. So 3 0 A alpha 1 plus alpha t squared minus or plus this, which becomes minus. So it is rho 0 A alpha divided by 1 plus alpha t squared, which is 2 0 A alpha divided by 1 plus alpha t squared. All right, so next part is actually wants us to calculate the total mass at time t And we also would like to know the reference time. At the reference time, t equal to 0, that was in control volume, which basically wants us to calculate the capital M. So it's over the material volume. So it is x1 and x2 capital and t, which was the integral of rho x and t dv x1 1, x2 2. Then we know that these are functions of x1 1 t and x1 2 and t. That's why we write this from so if we go here, 1 plus alpha t x1, so 1 plus alpha t x1 1 to 1 plus alpha t x1 2 basically. And then we have rho, which is rho 0 divided by 1 plus alpha t. We have dv is a dx1, and we know that a is the same as, a that we had in volume control. So this is going to be equal to the integral. So here it has the same length, like it starts from 1 goes to 3. So then we will have x1 1 equal to 1 and x1 2 equal to 3. So it is 1, let me just write it, 1 plus alpha t. Then we have 3, 1 plus alpha t in here. So this is rho 0 divided by 1 plus alpha t a dx1, which is equal to rho 0 a divided by 1 plus alpha t. So if we take this, this is going to be x1 goes from 1 plus alpha t to 3 times 1 plus alpha t, which is equal to rho 0 a 1 plus alpha t. This is 3 plus 2, so it becomes 3 minus 1, so it becomes 2. So 2 1 plus alpha t, so this cancels out this one, just 2 rho 0 a, which is our mass, total mass in reference time. So the last part actually wants us to calculate the total linear momentum. So total linear momentum of the fixed part of the material in part E. So basically here we have linear momentum, and this is a fixed part, and it was in part E. So since we are in part E, we are in reference configuration. So if you remember, linear momentum was mv, right? So here we can write the integral of rho x and t vi dv, changing from x1 to x2, so x1 1 to x1 2. So again, we have this x1 1, x1 2. Instead of rho, since this is representing m basically, and this is v, so this is the linear momentum. So then we have rho, which was rho 0 divided by 1 plus alpha t, and the only component of v which was not equal to 0 was basically v1. The rest are 0, so we only have v1 e1, because we know that this is a vector. So basically then we have dv, which was a, and it is in x1 direction. So if I take out this e1 in here from the integral, Now I write down in here, so instead of x1, I write 1 plus alpha t. So because we know that this small x1 is a function of capital X1 and t, so I'm gonna change the range of the integrals from to this 2 in here, and basically replace x1 and x2 with 1 and 3. So then I have rho 0 a divided by 1 plus alpha t. Then I'm gonna have v1, and instead of v1, I'm gonna write here alpha x1 divided by 1 plus alpha t. So we have alpha t, so it's going to be x1 alpha 1 plus alpha t dx1. So this is e1, the integral 1 plus alpha t, this is 3, 1 plus alpha t, rho 0 a alpha divided by 1 plus alpha t x1 dx1. So if I take the integral, so I'm gonna have like rho 0 a alpha divided by 1 plus alpha t. This is a squared. Then I have x1 divided by 2. This is e1, of course, from 1 plus alpha t to 3 times 1 plus alpha t. This is equal to, so this is going to be e1, and this is rho a alpha divided by 1 plus alpha t squared. 2 goes in here, and this is of course squared, sorry about that. So we have 9 times this squared minus this squared, so it's going to be 8, 1 plus alpha t squared. This goes with this goes with this, so we have 4. Finally becomes rho 4 rho 0 a alpha e1.